this video, I'm going to show you how to derive the key results for elementary inverse functions using the chain rule. So here we've got this example: if y equals arc sine x, calculate dy dx. So we know how to differentiate sine, but not arc sine. That looks a bit challenging. And we'd rather not go back to the difference quotient because arc sine is a pretty tough function to work with. How about let's turn this into a sine problem instead of an arc sine problem, and then we can leverage the chain rule. To turn this into a sine problem, we can just apply sine to both sides of this equation, and that'll cancel out the arc sine. So we'll just have sine of y equals x. And now we can take the derivative of both sides using the chain rule. So let's just write that out explicitly. D over dx of sine y is equal to d over dx of x. Alright, so here's where the chain rule comes in. Want to differentiate sine y with respect to x? Well, why don't we differentiate with respect to y first, d over dy of sine y, and chain rule says that's all good as long as we multiply by dy dx afterwards, so the dy's cancel, and we'll just have our d over dx as we originally did. Okay, so that's what the left-hand side will turn into. And the right-hand side is easier. We can just evaluate that derivative of x is just 1. Now, revisiting the left-hand side, that's easier to differentiate now that we've applied the chain rule. So d over dy of sine y, that's just cos of y. So cos of y times dy over dx equals 1. And then we can solve for dy over dx by just dividing by cos y. So dy over dx is just 1 over cos y. We're close now, but we're not there yet. We still want our answer to consist of just x, and right now we have a y in our answer. So we want to express cos y in terms of x. So that's what we're going to do next. Next, we're going to focus on expressing cos y in terms of x. Alright, so how do we do this? Well, we know what sine y is in terms of x. Sine y is just x. So if we can get something relating sine y and cos y, then we can express sine y in terms of x, and let's just solve for cos y. So how about, do we know any identities involving sine y and cos y? How about the Pythagorean identity, sine squared of y plus cos squared y is equal to 1. Alright, so sine of y is just x, so that's going to go in for sine of y here. We'll just have x squared here. So x squared plus cos squared of y equals 1. And then to solve for cosine of y, we can just subtract off the x squared, get cos squared y equals 1 minus x squared. Then we take the square root, get cos of y equals plus or minus root 1 minus x squared. But hang on, that's two possibilities. That's one possibility, cos y equals positive root 1 minus x squared, or cos y equals negative root 1 minus x squared. So which possibility should we use in our derivative here? It really does matter which one we choose, because if we choose this one, cos y equals root 1 minus x squared, that's positive, so that'll make our derivative positive all the time. Whereas if we choose cos y equals negative root 1 minus x squared, that's negative, so that'll make our derivative negative all the time. So really we have to think, is arc sine, does that have an always positive or an always negative derivative? Is it always increasing or is it always decreasing? And to figure that out, it might be helpful to draw a graph of arc sine, just a rough sketch, so we can tell whether it's always increasing or always decreasing. In order to draw a rough sketch of arc sine, we'll need a few points for sine. So how about with sine of 0, that has to equal 0. What else do we know? Well, we know that sine of pi over 6 is equal to 1/2, and we also know that sine of pi over 2 is equal to 1. Likewise, we know that sine of negative pi over 6 is equal to negative 1/2, and sine of negative pi over 2 is equal to negative 1. And so when we draw the graph of arc sine, these become our x values here, and the inputs to the sine become the y values. Here, remember that just comes from if y equals arc sine x, then sine y equals x. So x's are the right column, y's are the arguments to the sine, and we'll just plot these points. So how about let's start plotting 0, 0, and then let's plot 1 pi over 2. So 1 will go over here, and then pi over 2 we can make right here. Pi over 2, 1 pi over 2 is right over here. Likewise, -1, negative pi over 2, so that's just pretty much the same on the other side. -1, negative pi over 2, except we're reflected over the x-axis. And then lastly, 1/2 pi over 6, so 1/2 will be right here. Pi over 6 is a little less than halfway up here, so about right over there. And then it'll be the same idea on the other side, -1/2 negative pi over 6, so a little less than halfway up. So something like that. And we see that this function y equals arc sine x is increasing the whole way. So we got to choose the possibility for cos y that'll make this derivative always positive. That's going to be this possibility right here. Cos y is just root 1 minus x squared. So we're going to sub that in for this cos y in our derivative now, and then we'll just get dy over dx equals 1 over root 1 minus x squared. And there we go. Finally, we've got our dy dx in terms of x, and there's our final result. Alright, so we now know that the derivative of arc sine of x is 1 over the root of 1 minus x squared. And the implicit differentiation argument that we used to find that result can be repeated for arc cosine and arc tangent as well. We won't go through that process here, though I encourage you to do so, but here we'll just go ahead and list the results for arc cosine and arc tangent as well. First of all, the derivative of arc cosine is just negative of the derivative of arc sine, negative 1 over root 1 minus x squared. And that might seem really strange that it's just the negative of the derivative of arc sine, but it's actually quite intuitive once you think about the relationship between sine and cosine. So this happens because cosine of x is equal to sine of pi over 2 minus x. That's an identity for cosine, and if you differentiate both sides of this identity and use the chain rule on that sine of pi over 2 minus x, you end up introducing a negative because -1 is the derivative of pi over 2 minus x. Alright, so takeaway for arc cosine is just to remember that the derivative of arc cosine is negative of the derivative of arc sine. So it's negative 1 over root 1 minus x squared. And then lastly, the derivative of arc tangent of x is equal to 1 over 1 plus x squared. Now that's a little bit less intuitive, but if you use the same implicit differentiation argument from the previous slide, then that's what you'll get. And I'd highly encourage that you remember these three formulae so that you don't have to go through that lengthy implicit differentiation argument anytime you want to take the derivative of arc sine, arc cosine, or arc tangent. Alright, here's another problem. If y equals arc tangent of 2x plus 1, we want to calculate dy dx. Now this problem's a little bit trickier because instead of just having an argument of x, this arctangent has an argument of 2x plus 1. So what do we do now? Well, this problem is actually pretty easy once we make a substitution and apply the chain rule. So the substitution that we'll make here is we'll let u be 2x plus 1. That way, dy dx is just equal to dy over du times du over dx. It's kind of like the du's cancel out. So let's go ahead and substitute into here. So dy du is equal to du over du of our expression for y in terms of u, which is just arctangent of u. And then we're multiplying that by the derivative with respect to x of our expression for u in terms of x. And u is just 2x plus 1. So let's go ahead and compute this. The derivative with respect to u of arctangent of u, well, just using our standard formula for arctangent, that becomes 1 over 1 plus u squared. And then multiply by the derivative with respect to x of 2x plus 1, and that's just 2. So just going and simplifying this expression, we have a 2 in the numerator, because it multiplies that 1, and then 2 over 1 plus u squared. And let's sub in for u in terms of x. U is just 2x plus 1. So that's squared. So there we go. There is our derivative dy dx. We can use this reasoning to come up with several formulae for the derivative of an inverse trig function with a linear argument. Let's go ahead and write these down. The derivatives of arc sine, arc cosine, and arc tangent of a linear argument ax plus b. First of all, the derivative of arc tangent of ax plus b is just a over 1 plus ax plus b, the quantity squared. You can see that in our solution here. A was 2, 2 appears in the numerator, and then full expression ax plus b, which is 2x plus 1, appears in the denominator. Matches up. Now, for arc sine, this is pretty similar. We still have an a in the numerator, but in the denominator, remember arc sine is usually root of 1 minus x squared. So when we change the input to ax plus b, we have 1 minus ax plus b squared. And lastly, the derivative of arc cosine of ax plus b. Well, remember, the derivative of arc cosine is just negative of the derivative of sine. So negative of a over square root of 1 minus ax plus b squared. So if you remember these rules, it'll speed up the process of integrating inverse trig functions with linear arguments. But if you ever forget, just remember that you can obtain the same results without too much work by using u substitution and using the chain rule. So now we know how to differentiate inverse trig functions. And in the future, we'll start to learn about some uses of differentiation, including doing some applied problems.